Picture the International Space Station. It can be hard to grasp the scale of a 400-ton laboratory floating in the dark. If you were to bring it down to Earth and set it on the ground, its footprint would easily cover a full-size football field. No rocket is large enough to carry a fully assembled station into orbit. It's simply too heavy. To solve this, engineers treated it like a giant modular toy, breaking the design into individual room-sized modules that fit inside standard rockets. This colossal assembly project officially started in November of 1998. On the snowy plains of Kazakhstan, a Russian Proton rocket stood on the launch pad, ready to carry the foundation, a cargo block named Zarya. Just 2 weeks later, an American space shuttle thundered off a pad in Florida, acting as a heavy-duty moving van to deliver the second module, named Unity. High above Earth, a robotic arm captured the two components and clicked them together. Over the next 13 years, that delivery process was repeated more than 40 times. A fleet of rockets ferried up massive solar panels, new sleeping quarters, and science racks, one flight at a time. Construction took place entirely in the freezing vacuum of low Earth orbit. International teams spent over a decade assembling the structure, module by module, until the individual parts formed a single, massive laboratory. So now we have this 400-ton structure assembled 250 miles above our heads. It brings up a very basic physics question. Why doesn't Earth's gravity pull it crashing back down to the ground? The truth is, gravity is pulling on it, right now. In fact, the International Space Station is currently falling. To understand how a falling object stays in space, let's look at this diagram. Imagine standing on a tiny planet. If you toss a ball forward, gravity pulls it downward, and it curves until it hits the dirt. But if you throw that same ball faster, its forward horizontal speed carries it much further across the landscape before it finally strikes the ground. Now, imagine throwing that ball so fast, around 17,500 miles per hour, that its forward motion perfectly matches the curve of the Earth dropping away beneath it. The ball is still falling, but it falls past the horizon. It completely misses the ground, traveling in a perfect continuous circle. That delicate balance isn't permanent, though. Even 250 miles up, there are stray atmospheric molecules that create drag, slowly stealing the station's speed. To keep from eventually hitting the Earth, it occasionally has to fire its engines to boost itself back up. When astronauts say they are orbiting, what they really mean is that they are falling so incredibly fast that they perpetually miss the ground. This circular falling path doesn't align perfectly with the equator. As we can see in this 3D model, the station's orbit is tilted at an angle of exactly 51.6 degrees relative to the center of the Earth. Why choose that specific, strange number? Why not just launch the station on a simple, flat path right over the equator, where the Earth's spin provides a free speed boost? The answer comes down to geography. Russia's primary launch site, the Baikonur Cosmodrome, sits far to the north at roughly 45.6 degrees latitude. In orbital mechanics, trying to steer a rocket into a path that is lower than the latitude of your launch pad requires you to burn a massive, wasteful amount of fuel just to turn the ship. To build the station together, the international partners needed a mathematical compromise. An angle of 51.6 degrees was high enough for Russian rockets to reach efficiently without wasting fuel, but still low enough that American space shuttles launching from Florida could safely carry heavy modules up to meet them. The actual path the station carves through the stars is a permanent physical record of that agreement. They put the project exactly where all the partners could reach it. That logistical compromise created a beautiful side effect for those of us on the ground. Because the orbit is heavily tilted, the Earth rotates beneath it in a way that lets the station sweep over a vast majority of the globe. Over the course of a day, its light path crosses over North America, Europe, Asia, Africa, and Australia. Because it is so massive, and because its panels reflect so much sunlight, you don't need a telescope to see their work. Step outside at twilight and watch the station fly right over your own neighborhood. All you have to do is look up and find a bright, unblinking star racing silently from west to east across the sky. The International Space Station stands as the most complex modular construction project in history. It functions because every independent component, designed on different continents, was engineered to fit perfectly into a single global design.
Do you have any ideas for my next video? Just write them down in the comments below, and I will explain it in the next one. Don't forget to like and subscribe. Thank you so much for watching.